Okay, Ben is a postdoc on doing Raman spectroscopy. He comes from geoscience.
Yes.
But has worked on glasses for a long time, but very much on silicate glass systems.
Yes.
And he learned with a different Raman teacher than I did, so in general we agree on the interpretation of Raman spectrum. But apparently there are some little views of how to explain some things. And probably both are just some approximations from different sides, and the truth is somewhere in the middle. So and this isn't the first time that different people interpret the same glass problem in different ways, but in the end, it's usually the results aren't that different.
Yeah.
And so it's just different way of doing it. So I did a lot of other glass systems as well, where I see that you will hear about the free oxygen and the oxygen. And there's something where when you come from a different glass system, it's not so easy to define what's a free one, because they are connected to other things, which the silicate people don't appreciate because it's not silicate. But we will hear about that.
I'll highlight some of these issues, and I've tried to skirt the main controversial parts, I will say. But I'll give you the basis definitely for silicates, and that's my background, as Doris mentioned. So I'm coming from the geoscience, pretty much all of my experiences in silicate glasses. So you'll see that it's heavily laden towards the silicate glasses, but there's examples of quite a variety of glasses you'll see later on. So I'm just giving you a primer of Raman spectroscopy and how we link some of the structures that we can identify using this technique to the physical properties and some other features in the glass. So the Raman effect was observed first by C.V. Raman with his student Krishnan back in 1928. They won a Nobel Prize for this work. It was actually theorized a little bit earlier, a few years, 1925, when the theory was actually developed. And its main use is for looking at different structural species and to investigate what's actually going on the much smaller scale, the micro scale, or I guess the nanoscale in these glasses. So, just a bit of review. You guys have seen in Doris's presentation this beautiful example of some Roman glasses from Thebes. And one of the first things that sticks out is that with Raman spectra, here's a Raman spectra, the intensity is on the y-axis, the Raman shift on the x, and I'll explain more of this in detail in a minute, but it's very easy to pick out the features related to different minerals and crystalline phases in a glass. So one of the main uses, one of the number one uses, is identifying what phases you have in your glass, or your, well, not in your glass, but in your glass ceramic. And you can do this in a matter of minutes. These spectra probably took 10 or 20 seconds if you have optimal conditions. So it's a very easy technique, quick to find out what you crystallized or what happened to your sample as you were processing it. And this is one of the main uses, at least to the first order. This is a picture of a rock, but you can think of it as a glass ceramic, or a ceramic, I guess. And you can easily see that there's many phases. So if you were to do this by chemical analysis with a microprobe, there's a lot of sample preparation. You would have to polish the surface, you have to coat it, you stick it under in the microprobe, and you will analyze each mineral separately. That will take the better part of a day. In a Raman, you have no sample preparation required whatsoever, and you can identify all these phases, as I mentioned, in a couple of minutes. So this is the real power of this technique at the very most superficial level. And just in case you're wondering how you interpret all these different spectra and different peaks, you don't have to worry too much, at least when it comes to mineral phases, because there's a database with over 14,000 high-resolution Raman spectra. In this database, which is the RUF database, hosted at the University of Arizona, they also have X-ray diffraction and chemical analysis with all of their Raman spectra. So it's very quick and very clear when you identify the main peaks of a given crystalline phase. Doris also gave a brief introduction on the differences between infrared and Raman spectroscopy, and we saw that when you have a change in the center of charge, in the change of the dipole moment, the vibrations are IR active, but you require a change in the polarization ellipse for the vibration to be Raman active. So that's where we stood at the end of last class. And for today, I'm going to talk about what is Raman scattering, what's the actual Raman effect that we're talking about, how do we assess the quality of the spectra, and what are some of the ingredients that going into making a good and getting a good Raman spectra. We use this, we've mentioned, we use this for probing the vibration and the structure of the material we're looking at, the glass or the glass ceramic. So I'm just going to give a brief introduction to what we mean by some of those structural terms that we've been throwing around throughout the class. And then in the second half of the class, I'm going to run through a bunch of different examples and application of Raman spectroscopy in all different types of materials at high temperature, high pressure, different compositions, and you'll see quite a wide variety. You'll also note that in a lot of these we have nice curved spectra, and you see people putting these peaks underneath and saying this is this species and this is that species. So at the end of the class, I'm just going to go through a few quick comments on curve fitting of the spectra and how you might assess when you pick up a paper whether that paper has something called a meaningful Raman assignment or whether they've just sort of followed what everybody else has done with no critical assessment of that. So I'll go through a few notes of that. And I'm going to take a break after the first three before I get into the examples and the curve fitting. So that's kind of the outline for today. So we've seen that it's a vibrational spectroscopy, and it's quite sensitive to all these different vibrational modes. By far, the two most important in terms of silicates are these two modes in here. And when you get into the phosphates, sulfophosphates, you'll see that we get some of the other vibrational modes as well. Doris presented this comparison last time, but I just want to highlight a few things that are different. Most intense, the first is, of course, the process is completely different. I'm going to go through that in a second. But the next is that we use monochromatic light, and we look at light that has a wavelength that's shifted from the excitation wavelength. So the light that's hitting your sample and the light you measure have a different wavelength. The next is the range. The IR is limited by air and the requirement for a vacuum. Certain wavelengths of light don't transmit through the atmosphere, but in Raman we're using optical light. We're using green, red light. These perfectly happy to go through air. They're perfectly happy to go through glass or anything else. This means you can measure a solid, a liquid, or gas even through a container. So I can measure the water that's inside this glass through the side of this, through the glass, and get a perfectly good signal without contamination of the glass itself. The last part, and we'll go through this in the latter part of the lecture, but we'll look at some of the effects of dopants, impurities, and we'll touch on the spatial resolution of this technique. So Raman scattering. Here is the Morse curve, where you have the distance from the nucleus and the different energy levels. On this curve, we can superimpose some vibrational energy levels. And when you have light that scatters through a sample, when you have light that photons that hit the sample, they mix with the electrons that are surrounding each of the atoms. When they mix, this excited state is called a virtual state. It's really fast. It happens basically instantaneous, and we have no way of actually probing it. It's mostly, no, that's all I want to say about that. So the majority of the light that hits the sample gets excited into this. So here's your sample down here. You shine some light, it hits one of these levels, it excites it to this virtual state, and the state decays and releases the light, and that's what you measure. The majority of the light comes off of the sample with the exact same energy that was shined on the material in the first place. This is called Rayleigh scattering. A very small proportion of light, in fact 1 in a million, will experience a shift in the frequency of the light or the energy of the light. So when a photon hits your sample, it excites to this virtual state, but it only falls back into the first vibrational level. So the energy released, the photon that's released and detected, has a smaller energy than the photon that went in. So it's lost a bit of energy. In even a more rare situation, you can excite this photon from the first vibrational energy level. It's excited and it decays, but it falls back down into the empty first level. So it's actually gained some energy. And how does that look? So we've talking about the different wavelengths of light and what we use for Raman. And we typically use blue, green, or red lasers. And a very simple review, that all of these wavelengths from blue around 400 nanometers to red around 700 nanometers can be described either in terms of their frequency, their energy, or their wavelength. And these are the equations down here for how you go between these different units. So the wavelength in nanometers is inversely proportional to the frequency. And it's related by c. This is the constant for the speed of light. The frequency is also related to the energy by Planck's constant. And sometimes you'll see, I put this down here, this is the angular frequency instead of the frequency of light. It's just related by this equation here. So sometimes for Raman spectroscopy, we measure the frequency shift of the light, but you should know that you can convert that to energy or to wavelength depending on what your use is. So depending on what paper you picked up from Raman, if you're in physics, typically they use energy more often, but if you're in earth sciences or chemistry, we'll use just frequency. So just to go through a quick example of the green wavelength, because this is something that sometimes trips people up. We can go from the wavelength to inverse centimeters in a direct way. And when you move from nanometers to centimeters, you get this number of nanometers is equal to this many meters. It's equal to that many centimeters. Very simple, straightforward for conversion. And all you do is take the inverse of that to get wave numbers. So the wave number for a green laser is 18,797 inverse centimeters. When we look at a Raman spectra, we usually look at the shift in this frequency, right? The Raman shift or the change. But we always have to keep in mind what our initial wavelength is. So at 0 on any Raman spectra is the actual wavelength of light of the excitation of the laser that you're using. So in this case, in this example, 532, it's equal to this many inverse centimeters. And in the relative scale that we use in Raman spectra, it's actually 0 Raman shift, because this is the Rayleigh scattered light. It's the same as your excitation wavelength. As you move across, we have the Raman shift, a light at different frequencies. So if we go over in this example, this is the spectra of pure silica, and we look at this band around 1,000 wave numbers. So in absolute terms, 1,000 wave numbers is this 18,797 minus 1,000 inverse centimeters, and you can convert that to wavelength. It's a shift of about 30 nanometers. But in relative terms, it's still 1,000 wave numbers. So throughout the presentation, throughout the papers, you'll see the frequency or the Raman shift or wave numbers, it's all the same. It refers to this inverse centimeters, and it's all relative to the excitation wavelength you use. At the top of this picture, I've put a bar of this 1,000 wave number shift. And in the blue range, if you're using a blue range, the shift, the wavelengths that are covered by the spectra of 1,000 wave numbers are shown here. And as you can see, with longer wave numbers, you cover a much larger proportion in terms of wavelength. So, do any of you have a guess? In terms of Raman Shift, will the band positions change if we actually use different excitation wavelengths? Any guesses? Because we have much longer scale for the same 1,000 wave numbers. In the spectrum, it's a smaller wavelength here and a longer wavelength there. And the answer is that the Raman bands won't change. But some other bands, and we'll see an example of this later on in the second half of this class, if they're related to fluorescence, they will change. So you can play around and avoid, if you have some really fluorescent samples, you can use different wavelengths of light to avoid that fluorescence and still get a high quality spectra. And here's an example of that. This is the mineral calcium taken from the database I mentioned earlier. And these are the different wavelengths of the excitation laser. And you can see that pretty much all of the peaks are in identical position in inverse centimeters. So this is why we use inverse centimeters and not absolute wavelength, because it makes the scale the same, no matter what you're using in your initial go. We also saw that some of these photons can lose or gain a bit of energy, these Stokes and anti-Stokes. So in terms of the Stokes side, we see that the photon has lost a bit of energy. It's at a lower frequency, or it's gained a bit of energy, it's at a higher frequency. These are the anti-Stokes and Stokes spectra. Here is that same spectra of SiO2 showing both the anti-Stokes and the Stokes side of the spectrum. One thing you can observe right off the bat is that the Stokes side is much stronger than the anti-Stokes in terms of intensity. And therefore, as a result, most of the time we use just the Stokes side of the spectrum because it's way more sensitive to the features that we're trying to look at. And don't worry too much about what these features are, but if we got equal amounts of photons that have higher frequency as lower frequency, the spectrum on both sides should be the same. And we see that's not the case. We also see that because it's lower, has a lower intensity, any of the features like this one here around 500 is much smaller. So one more reason that we use the Stokes side of the spectrum. I'm going to come back to the assignments later on. One of the ways we model what these vibrational frequencies are is using the harmonic approximation. So in the harmonic approximation, we treat this Morse curve as a simple parabola. And for most of the time, this works very well. Here, in this case, we use Hooke's law, which states that the frequency is related to a bunch of constants times the square root of k over mu. And k is the force constant, this is the strength of the bond, and mu is the reduced mass, which is given here. So the mass of atom A times the mass of atom B divided by the sum of those two. So what's your prediction about the frequency if we increase the mass of the atom we're looking at? So take, for example, a substance where we substitute germanium for silica. What do you expect for the shift in the peaks? Come on. Yeah, exactly. Perfect. So here's two spectra of a diopside and a germanium diopside, calcium magnesium silicate, calcium magnesium germaninate. We can see that if you just look at the spectra, there's the same overall pattern. We have some peaks. There's some subtle differences here, but we have two major peaks with a couple small ones in between. In the low frequency part of the spectrum, we have two major features at much higher wave numbers, and we can see that the sample with germanium, the frequencies are all shifted, all compressed towards lower frequency. So this actual fact was what was used to identify some of these weird features in the silica spectrum back in the early 80s. This is that same spectra of SiO2, and again, don't worry about the assignments, we'll come back to them. But Galiner and co-workers, they substituted heavy oxygen and heavy silicon isotopes into the silica structure and looked at the shift in position of all these main features. And this allowed them to identify, are these vibrational features associated with silica, oxygen, or some other defect or something else that's going on in the system. So in pure silica, for example, the peak here is at 495. In the oxygen substituted spectra, it's at 465, and in the silicon spectra, it's at 485. And you can see some other examples, but you see this isotopic shift. So this spectroscopy is really sensitive to the isotopes in the system. I think you may have seen this example already, but I'll go through it again. We see one of the main symmetric stretching in CL4, so CCl4. And if we zoom in on this peak, what we see is that there's actually 4 different peaks underneath it. And if you look at the isotopes of chlorine, we have chlorine 35 and chlorine 37. And as you increase the proportions of 35 and 37, 137, 237, 337, 437, we have this linear shift in the peak. So we can actually use these isotopic frequencies to identify what vibrational modes are there and to assess the effects of isotopes in the system. So just to run through the actual experiment, you don't need any actual processing of the sample. You just take whatever sample you have, you stick it on a microscope stage. Light is directed onto this sample from a laser and scattered back through the Rayleigh rejection filter. It's taken by a lens onto the grating and then focused onto your detector to get the spectrum. And I mentioned this before, but I'd like to emphasize the fact that you can use this on any state of matter. It doesn't matter, liquid, gas, powders. So long as you have a transparent container, you can measure what's inside of that container using the Raman system. There's a bunch of different wavelengths we use and a variety of geometries. The main different uses of the different wavelengths are for blue and green lasers in the higher frequency part of the spectrum. They're good for inorganic materials. These are the ones we typically use for silicate glasses, but it's also used for a couple other techniques. In the red or infrared, it's good for fluorescence suppression. And at the ultraviolet, we can use it for biomolecules, proteins, and looking at DNA. So pretty much any material you want to look at is possible in any state, whether it's biological, inorganic, whatever you like. Just to mention, I'm only going through classic Raman scattering today, but there's a huge number of Raman techniques that have been developed over the years for different applications. You have hyper-Raman scattering, you have coherent anti-Stokes scattering, you have TIRS, which combines Raman scattering with an atomic force microscopy. But there's a bunch of other techniques depending specifically on what you want to look at. So just be aware that it's been, the technique of Raman spectroscopy has gone through a lot of evolution and found uses in every corner of the science world. So a few comments on the quality of the spectra. If you look at these spectra, which are published, they look quite noisy. And if you're trying to model what is under this curve, you can fit a lot of different peaks in a lot of different positions. So the goal in getting a good quality Raman spectra with a very straight line, you have to adjust some of the factors that are listed here. So first of all, the quality of your overall detector, the quality of the lens you're using, the different gratings all go into improving the signal to noise ratio. How much light, which is controlled by the confocal hole, how much actual light is scattered off your sample and received by the detector, what objective you're using, what wavelength, and this is really important, we'll see in a second. The surface of the sample, if it's not perpendicular, you're going to get a lot more scattering off to the side and the detector's not going to see that. Sample color, homogeneity, the refractive index, all of these factors you really have to get some experience with to determine what's best for your sample. So it does take some trial and error at the beginning. Or you work with somebody who's an expert who already does it with that specific application, and then they save you a lot of time. So looking at the intensity, it's proportional but not directly proportional to the excitation wavelength. So the laser that you're using for the samples, some lasers are good for some samples. We mentioned ones that are good for biological materials, some that are good for inorganic materials. That excitation wavelength goes to the power of 4 in terms of the intensity. So it's really important in choosing the right laser for the job you're looking at. Also, how intense the excitation is, so how much light you're actually getting on the sample, how much power is in your laser, how many molecules you're actually sampling, and this change in polarization, which goes to the square. And we're going to see how this polarization changes for some of the materials, specifically for silica, and then anything you add to the silica. So the most important factors, this polarization and the frequency of the laser you're using. A lot of people use a correction on the spectra. So you take a spectra and it looks something like this top one here. Most Raman spectra of glasses and amorphous materials have an enhanced scattering up here. And if you get a modern Raman system, it has nice edge filters or triple gratings, and you can get down really close to the wavelength. So this is around 10 wave numbers here. But the older systems, they couldn't get that far, so they rejected pretty much everything from around 150 wave numbers lower. So if you want to quantify the spectra and you don't know exactly where this line comes, you have to make a guess about where is flat in your sample. So at the beginning, they didn't know where this came from, but they made the observation that it was very sensitive to temperature. Now, the whole point of this correction was originally to get rid of this wild slope, and you can see the corrected spectra, reduced intensity spectra here along the bottom. It looks much nicer to deal with, and you can easily say, hey, there's a straight line somewhere in here to take off the background of the spectra. Fast forward through some time and getting better equipment, and we see that this peak is actually a real thing. It's called the boson peak. Its origin is debated, and I'm not going to get into that debate here. But it's really strong, has a really strong sensitivity to temperature, and you can actually use this to back calculate to 0K and look at the intrinsic disorder of your sample. So this intensity correction was used to eliminate essentially what is the boson peak. And it was so popular, everybody still uses it, but now that we know it's a real thing and we can take some stabs at modeling what's going on with this peak, it may or may not be so applicable. I mention it because a lot of people just do it by default because so many people in the literature have used it. So just to highlight that sometimes the spectra is corrected, sometimes it's not. And if you want to compare spectra, you have to treat it in the same way. So if what you're looking at, what you're trying to compare has been corrected, then you should probably correct yours. Or maybe try to do it with the correction, without the correction. In terms of the sampling volume, there was a question last class about the spatial resolution of it. There's two factors. One is the actual spatial resolution in terms of where you focus your beam, and the other is called the depth of field. And these combined give you a very crude estimate of your actual scattering volume that you're sampling. So for the spatial resolution, the width of that beam is related to 1.22 times the wavelength of excitation divided by the numerical aperture. So here are some typical wavelengths. Here are some different objectives you might be using. This is the numerical aperture that's written on the side of every objective. And you can see that at a 50 times objective using our green laser, we have a horizontal distance of about 2 microns. That's your spatial resolution. If you go up to a 90 times objective, for that same green laser, we're down below 1 micron. So if you have layering that's 1 micron thick, you can actually isolate those individual layers, in theory. And then if you switch to a red wavelength, we can see that our resolution increases a little bit more. The depth of field, how deep of the sample you're exciting, is equal to 4 times the wavelength divided by the numerical aperture squared. And so you can see again, with our green laser from 50 to 100, we go from about 18 microns down to about 3 microns of sampling depth. Again, this is a pretty crude estimate, and it really depends on what is happening in your sample. If you have crystallization that gets in the way, if you have other heterogeneities, it depends on the refractive index of the sample. If you have a lower refractive index and laser can shine deeper, the photons from deeper and wider all around this area can get out and contribute to your spectra. But this gives you a nice first order guesstimate of the spatial resolution of this technique. If you look on the left, this is raw spectra of a variety of sodium silicate glasses. The red here is pure silica. We've seen a couple times and we'll see a couple more. And then as you add sodium down to 50% sodium, which is this spectra here. This spectra are probably taken under the exact same conditions, but with a slightly different focus. And you can see that the pure silica sample has a much lower intensity overall than the sodium-rich sample. So this is related to that polarizability of the vibrational modes you're looking at. So we need a way to get around the fact that every time you make a new measurement, your spectra will be a little bit different. So we have to normalize the spectra in some way, somehow. The most common is by normalizing the intensity of your spectra to the maximum intensity peak. So whatever your intensity is here, this is the maximum intensity peak, and we make this intensity 1 and make all the other intensities in the spectra relative to that most intense peak. And you can see when you go from the left to the right, you have a much better looking spectra, and you can see that there's clear shifts in where the peaks are at and where they go as you add sodium to the sample. You can also do an area normalization. You can say all the signal we're getting is equal to 1, and then area normalize it as well. We'll see an example where this comes into play in the second half. But you should know that most spectra have been normalized and treated in some way, and when you're reading the paper, they should make it clear how they've done that normalization. The bottom line is that the relative intensities of these peaks are what's important and not the absolute intensities. Another thing to look at is that a lot of peaks are either polarized or depolarized. So in the polarization process, if you have light that's vibrating in one direction, you can measure the light that's scattered back in the same direction, or you can put a filter that rejects all light except in a specific orientation. So the initial scattering light might be vibrating like this, but you might only look at light that's scattered horizontally or perpendicularly to that. So a lot of spectra have VH, so this is the horizontal versus vertical, and or measured in the same direction, HH. In the same direction, this HH spectra, you get a nice, really strong spectra, but in the horizontally polarized one, you have much reduced intensities. And if you take the ratio of those, the depolarized over the polarized, you can see that these major features in silicates are quite polarized. They have very low depolarization ratio. So this leads Almeida and Santos to say that for silicates, most of the vibrations are strongly polarized, and the interpretation is that most of what we see is related to symmetric stretching mode vibrations and not all the wagging and the other vibrations that we showed early on. So if you have more complicated samples where there's a lot of band overlap, you can look at the depolarization ratio to get an idea of whether the band might be coming from, say, silica or titanium or something else like this. So it helps you distinguish the band positions when you have big, broad bands that have lots of overlap. So with that introduction about the spectroscopy, I'd like to just stop for a second and give a brief intro on glass structure. You'll see that we talk a lot about QN species and different structures within the sample you're looking at. And I want to go back to one of the first examples for how crystals differ from amorphous systems, and this is called the continuous random network. It was developed by Zachariasen in 1932, and he said in contrast to crystalline materials, where here you can see nice, this is a silicon, these are oxygen, and there are 6 member rings that cover the system. So this is sort of cristobalite-like structure, but don't worry too much about that. But with minerals, you have a nice ordered system. This is why you get nice sharp diffraction peaks. When you go to an amorphous material or a glass, and Zachariasen was thinking specifically as SiO2 or B2O3, you have different distributions of ring sizes, and you have large voids and some small voids, and you get a wide distribution of these. Not much changed about this model for a very long time, but one of the interesting developments was that back in 2012, Huang et al., they used a TEM to actually image the crystalline and non-crystalline parts of a material they were working on. And this is a great example of luck. They were actually looking at carbon, bilayers of carbon on a surface, and they happened to sputter some silicon onto their carbon layers, and then, oh, they got beautiful images of really well-ordered material that looked almost identical to our crystalline model, and they got disordered areas that looked almost identical to the amorphous model. And they said, okay, Zachariasen, back in 32, he really knew what was going on. If you actually zoom out, and he has a nice, in this paper, there's a nice big figure here, there's a couple problems with saying that this is the same as this. And the biggest of these is that in this image, if you look closely, and I stared at this for hours, you don't get any 4-member rings, and you don't get any 3-member rings. So it's very close, but there's some things to be cautious about. I put this in here to give you actual definitions from George Callas and other workers. I'll leave it to you to read through these as you need them. I'm not going to go through them, but you'll have them to read after the class. But I'm going to talk about some of the key aspects. For instance, the network formers, the network modifiers, and the different types of oxygen we get in the silicon network. So I mentioned Zachariasen. He had this idea about pure silica, SiO2. And it took about 50 years until the early 80s for Neville Greaves to come up with the first substantial evolution of this idea, and he called it the modified random network model. And he said, as you put these atoms like sodium or potassium, these network modifiers, they typically have weak, more ionic-like bonds, and so they have to break up this SiO2, these strong covalent bonds, in some way. So I'm going to talk about exactly how that happens in a minute, but the idea was, the conclusion was, that you get some channels. If you have lots of modifier, you get channels with modifiers that break up. These are the weak ionic-like bonds that break up this silica network that is much stronger and made out of covalent bonds. So let's go through in a little bit of detail what is actually going on in this photograph, of this model. First thing you have to remember about all these are that they're 2D and not 3D. So we're missing a dimension of reality, and you have to keep that in mind. And sometimes it's pretty difficult. If we look first at the bridging oxygens, some bridging oxygens, for example, 1, 4, and 5, so here's 5. This guy is only bound to other silica atoms. This guy as well. If we look at some of the oxygens around the margins of this silica-rich network, for example, oxygen 2 here, it's bound to 2 silicons, but it also has to have this modifier sitting beside it. So this is the major development by Greaves. He said these modifiers, they actually have some order, and if they have a coordination number of 6, typically 6 to 8, they must be sitting next to some bridging oxygens. So that was a big deal, because it means that you have to take this into account when you're making any model. You can't just say the oxygen is bound only to silicon. It has to be taking into this modifier effect that's sitting nearby. This year, Nesbitt and coworkers, they observed a third type of oxygen. And this is where Doris and I may get into an argument. No, I'm just kidding. But they showed there was a third type of oxygen. Some of the oxygen in the network might only be surrounded by sodium ions. So this is oxygen that's not bound to the silica part of the network. It's just held in the network by these weaker ionic bonds. They term this free oxygen or free oxide. Other people have called it non-network oxygen because it's not part of the silica network. It's sitting in these channels. So whatever name you prefer, it doesn't matter. Just define exactly what you mean. Because the big confusion arises when you say O2 negative, this could be an oxygen atom that's not bound to the network. This is a free radical. So for me, the free oxygen is a little bit confusing, and non-network oxygen makes more sense. And this is oxygen that's only bound to the network modifiers. Okay?
And that's I'm coming from the other side, looking at niobate classes and antimonate classes in those intermediate oxides. So yes, if you're talking about oxygen with a sodium, then yes, that's a modifier of whatever connected oxygen. Like even aluminum and lead, at some point they're forming their own polyheders. So the free oxygen making a lead tetrahedra, it's connected to something, and with the niobates it's the same. And there are people who come from the niobate side, doing Raman niobates, and then they say, oh, the niobate has a non-bridging oxygen that's connected to silicate. And there is some inconsistency in the sentence, a non-bridging oxygen connected to silicate, but there's a focus on discussing the niobate structure, that everything not connected to another niobate is non-bridging, even if it's a strong bond to the silicate. So it depends where you're coming from, and sometimes they write it like this in the paper and then you know what they mean, but if they just say non-bridging oxygen, they don't care at all if it's connected to sodium or silicate.
Yeah.
Then you're into trouble and you have to ask.
So there's some work to do for you guys to straighten out this. Hopefully you guys are coming from different ends of the spectrum. But something to be aware of, definitely something to be aware of when you're looking at models and reading papers specifically from, say, geoscience versus physics or versus molybdenates versus silicates. Different people have slightly different definitions.
People who use a different nomenclature than you do. Just try to figure out what they really mean and how that goes into use. And then it can be really helpful to you, even if the language is different from what you're used to do. Just try to understand what they mean. And then use the meaning if you don't want to use the word.
And please say exactly what you mean when you publish a paper and use these terms. One of the other features is that we can look at is looking at this silicate part of the network. So in this case we have sodium potassium in the network. Here I've taken a picture of a 2D image of it's an imaginary image, of course, that I made, of diopside glass, this calcium magnesium metasilicate. And we actually get different vibrational frequencies from tetrahedra that are bound to different numbers of other tetrahedra. This is that same, in the most general sense of the term, it's the same as that mass effect. So what do we mean by the QN species? In this glass, there's no Q0s or Q4s. This is a silica tetrahedron with 4 oxygens surrounding it, and they are only bound to network modifiers. There's no bridge to another tetrahedron. If we go up one and we go to a Q1 species, this is a tetrahedron with 1 bridging oxygen. Here's an example here. Remembering that this is in 2D, not 3D, but this is bound only to 1 other tetrahedron. So this is what we call a Q1 species. We can have tetrahedra that are also connected to 2 in what some people might call a chain, but you probably shouldn't use that word. Or you can have connections in 3. And we can also see maybe there's a ring here or something going on. But this is what we mean by the QN species. The N in this refers to the number of bridging oxygens, 1, 2, 3, and Q4 species with all bridging oxygens to other tetrahedra or network formers. What has to actually happen when you add these modifiers to the network? This is quite important in how you view the system. If you have pure silica that only has bridging oxygens in it, every other tetrahedra is connected to another tetrahedra, and you add some modifier, for example calcium. With that calcium comes an oxygen, and this is the sort of free oxygen that those guys are talking about. So it's not totally free in the network. It's bound initially to this calcium, but then it reacts at high temperature when you melt the system together, and you have to produce non-bridging oxygens in the process. So if we look at the different proportions of the oxygen species, as you take pure silica and add a modifier, you have to produce continually more non-bridging oxygens to the tune of 2 non-bridging oxygen for every bridging oxygen you break. You have 1 bridging oxygen, you break that bond, you need the extra oxygen here to join the tetrahedra that's lost in oxygen. So you produce 2 non-bridging oxygen. A lot of people assume that this reaction goes to completion. So as you increase the non-bridging oxygen, this is the bridging oxygen curve here. We have 100% bridging oxygen in pure silica. As you add modifier, the bridging oxygen should all be consumed and turned into non-bridging oxygen if this reaction goes to infinity. So if all of the modifiers are converted to NBOs, and you will predict this curve here. As a consequence, the non-bridging oxygen starts off at 0. If all of the bridging oxygen, all the modifier oxide turns into non-bridging oxygen, it will go to 100% at the orthosilicate composition. And I'll show you an example of that composition, but it's whatever the modifier is, 2 times whatever the modifier to 1 mole of silica. So 2 moles of modifier to 1 mole of silica. So if this reaction doesn't go to infinity, that has a couple consequences. The first off is instead of only producing free oxygen until after all of the bridging oxygen is converted to non-bridging oxygen, we produce this non-networks oxygen at much lower compositions. And in a lot of papers, something to be aware of is that they've assumed that this reaction goes to infinity and that there's no free oxygen in these intermediate compositions, but there should still be a tiny fraction even as soon as you add a modifier to your pure silica network. So depending on which assumptions you make, your proportions of bridging and non-bridging oxygens, especially around these intermediate compositions, if you assume it goes to completion, your bridging oxygens or your non-bridging oxygens can be 100%, but if it's not the case, it doesn't go to confusion, you can be off by up to 20% here. And of course, this gets much smaller as you go away from it, which is why one of the reasons why it hasn't been paid too much attention in certain literature. So you can be off by some non-trivial amounts depending on what assumptions you make about adding modifier to your glass. But this reaction is the key one that you can use to cover your entire range from pure silica to 100% modifier.
Do you bring the example of the lead?
No.
Because lead is a very typical example of doing a lead oxide pseudophase, which in the end would be, you have lead oxides just connected to lead oxides, so they store all the free oxygen. And it's in lead silicate glass or lead boron glass, and it has been termed the lead oxide pseudophase, actually. And you will see that there's less modification of the silicate in the boron network. So that's a very famous example, but it's, yeah, I would say you have lead oxide tetrahedral, and so it's not exactly free and it's intermediate whatever oxide, but it's exactly what an example of this thing, that you don't have a full conversion of the silicate or boron network.
So, where we get into trouble with this conceptual model of adding modifier and converting bridging oxygen into non-bridging oxygen is twofold. First of all, when you have very low silica and high modifier contents, you have potentially, or not potentially, but most probably, very high amounts of this free oxygen or non-network oxygen in your glass. This is extremely difficult to measure. There's literally only a handful of studies that have measured the amount of this non-network oxygen in the literature, at least to my knowledge, of silicates, I should say. So it's very difficult to actually measure this. So you need some end around to get at this information, and that's if you can figure out your rate constant here, then you can actually calculate this non-network oxygen from the proportion of bridging and non-bridging oxygen in the glass. On the other end of the spectrum, when you have silica-rich glasses, the problem is with the Raman intensity bands, and that's because these Q4 species, we saw in silica that at the high frequency range, and I'll show this now, in the high frequency range in pure silica, we have almost no vibrational modes. But as soon as we add even a little bit of sodium, we get quite strong peaks here, and these are the vibrations, the antisymmetric vibrations associated with the different QN species. Q4 being at the highest frequencies and Q0 at the lowest frequencies. So there's a problem here. We can't actually, with Raman spectroscopy anyway, you can with NMR, but with Raman you can't actually determine the proportion of Q species directly from the spectra. Or you have to make some assumptions about the behavior of those Q species in your spectra. So we see here nice for pure silica. The reason why we get such a strong such a strong band as soon as you add sodium or any modifier in this region is not really known. But after 5%, the intensities seem to be proportional, and we can make a nice model about going from, as you increase the modifier content, going from Q3s to Q2s to Q1s and so on. So you need to make some assumptions about those Q4 species. I'm not going to go into that because everybody does it a little bit different for silicate glasses, but you should be aware that it's really difficult to actually determine the proportion of Q4 species. So if you think you have here Q4 species and Q3 species, you might only get one band from the Q3 species. So you need some other way to test your assumption about how many QN species you have and how much bridging and non-bridging oxygen you have in the system. I'm going to go through this example pretty quick, but it's a good test for whether you have the right proportions of non-bridging and bridging oxygen and the right Q speciations as a result of this. And this is relatively new. It only comes from a couple years ago. So it still has yet to really be tested whether this is legitimate, but it looks pretty good at the face. So you need two things. You need one relationship between the proportion of the oxygen species and the molar proportions in whatever your glass is. And to start, we have to look at the molar proportions of bridging and non-bridging oxygens. So for bridging oxygens, a Q4 species has 4 bridging oxygens, Q3, 3, and so on. For non-bridging oxygens, the opposite is true. A Q0 species has 4 non-bridging oxygens. A Q4 species has no non-bridging oxygens, so I've ignored it here. And you can look at, uses this ratio X. And the total molar proportions of oxygen should be your bridging oxygens, your non-bridging oxygens, plus your non-network oxygen. For orthosilicates, this is the composition here. We have for every silicon, we have 2 times 1 oxygen plus 2 more oxygen. You get 4 oxygen total. Metasilicates 3, disilicates 2, and so on. So if we can't measure this O2, this non-network oxygen, how do we go about doing that? I've done a little example here of calcium metasilicate, so CaSiO2. Here's our proportionation between the moles of bridging and non-bridging oxygen. And I've taken this composition this speciation for this glass is an interpretation of a Raman spectra determining the Q1, 2, and 3 in this glass. You notice that there's a little bit of error here. It doesn't add up to 100%. It adds up to 0.99, so take that into consideration. But you can chug through the simple math, and you can see that the molar proportions of bridging and non-bridging oxygen are 1.1 and 1.7. So the first check is, do you get a reasonable value for the molar proportion of non-network oxygen? So going back, metasilicate is 50% modifier, 50% silica, and we said we have, oh, that's in proportions, that's for the first part. Sorry. But whether you get a positive value or 0, if you get a negative, something is seriously wrong. The other relationship is this equation up here, which relates the total moles of silica to the oxygen, to the proportion of free oxygen. Again, I'll let you do the math. It's pretty straightforward there. But if you get a negative number, your model is incorrect. And you'll see in some papers, they recognize that they got too much bridging or non-bridging oxygen, and they made a little correction, or they said, oh, we made this assumption. And then they changed their model to actually fit. So when you're fitting your spectra, when you're trying to determine QN species, and when you're reading a paper to evaluate whether that composition you're talking about actually has a reasonable model, you should use their QN speciation value and calculate these two things to see if you get a non-negative value. And then you can look at, did I put it here? Yeah, sorry. Then you can look at a diagram like this, and you can make it for any composition and see, yeah, do I have actually very low amounts, very low proportion of non-network oxygen? So those are two good tests as far as I'm concerned. The next thing I want to look at is where these ideas about QN species and the structure came from. And this is a classic paper from Brower and White in 1975, and they took potassium, sodium, and a couple other compositions and made glasses from the mineral and melted them for a while and then quenched it really fast, just in your standard process. And what they observed, here they have the frequency shift, and here the excitation line 0 is over here, and it increases that way. For some reason, people plot it 0 at one side or the other. It doesn't really matter, so long as you can compare in the right way. So the main features of any crystal, these very strong bands, appear to be the same as the glass. The positions are very similar. You see 585 versus 595, 963 versus 967. And there's lots of other bands in here. These are lattice modes of the crystal, which we don't actually see in the glass. But we have some other vibrations in this region as well. And the key feature that they observed is that for this high frequency band, this is where those QN antisymmetric stretching vibrations are, they get a lot of other vibrations. You see a big shoulder here that's quite wide. This is, over 100 wave numbers here. So they have to, the glasses and the crystals have to be sharing some characteristics of each other, but in the glasses there's something else going on. And of course they had in their mind that when you go from crystal to glass, you get these different sizes of rings, you break up the network, and so maybe there's some other features in here. This is some work originally done by Macmillan. He was kind of the pioneer, at least on the geoscience side. And they plotted the position of these high frequency band. So frequency is now increasing on the y-axis. This is the amount of modifier. And they showed for about 25 different crystal compositions in these circles, they actually sit almost on top of the glass compositions, the glass values for the same composition. You can see there's a little bit of spread here. In this case, for Q2 or Q3, there appears to be the most. It's about 50 wave numbers or so. So there's a little bit of play in here. There's a little bit of changes. But these results are pretty good. So the main dominant structural unit, the main QN species that's found in the crystal, is the same main dominant species found in the glass. And they've redone this for more glasses. And the other thing that these guys added is they actually compared the stretching frequency for these Q species to, this is the same Y scale, but this is the binding energy of the 2p electrons. And I'm not an expert in XPS, so I'm not going to go through what this means, but they created this relationship to actually determine the strength of this, the vibrational frequency of the QN species as a function of the number of bridging oxygens. And this has been done for potassium and sodium, but it's still an open area of research that's going on. But this is to point out that there is this relationship, a direct relationship between the frequency in the Raman and the actual strength of the bond between the different QN species. There's a little bit of shift, but not that much. So, in terms of silicates, if we look at a Raman spectra, we can talk about a few different things. The first is the QN species, and we'll see more of this later on, but they're in this high frequency range. In really silica-rich compositions around 800, there's a band. It's called a cage rattling band. It's not really well defined, so I'll leave it at that. But we also have vibrations down here from the bridging oxygens, and these span quite a wide range. You've seen in pure silica, they have a large band here, 200 to 500, and as you go to more metasilicate and more modifier-rich compositions, these BO vibrations go to higher wave numbers. So Raman spectroscopy can give us information ultimately about this QN distributions. There's some studies that have attempted to determine the intertetrahedral angle changes with that. We can also look at some ring structures in the glass, and we'll see some examples later on of the influence of different cations and dopants in the glass. This is just a summary figure. Don't worry too much about it in terms of trying to pick things out, but here's silica-rich compositions at the bottom. Here's sodium, lithium, potassium glasses, barium, calcium, magnesium glasses. All the dominant alkaline and alkaline earth silicates share some similar features. As you get to higher modifier contents, as I mentioned, these bridging oxygen vibrations move to higher wave numbers. As you go to silica-rich, they tend to have this tail towards the low frequency end. And we can see that the Q speciations has some pretty strong variations as you go from Q3s and Q2s down to Q1s and Q0s. So this is a view of the spectrum. We'll see that actually in the case when you switch silica for germanium, you actually get the same overall vibrational shape of the spectra. So the same structural units determined for silica, which is by far, to my knowledge, the most studied system, are applicable to the germanionates and other more exotic compositions. So before I take a break, I'll just go through a few more slides, but let's look at the actual spectrum of silica since it is the most studied. This really broad band, it's not 100% clear that it belongs to one specific bridging oxygen vibration, but it probably represents that. It probably is related to a symmetric stretch as well as some rocking motion within the network. And lots of people have made attempts to model this, and they get a pretty reasonable fit for this, but it's so broad and has such a varying shape, especially when you start to add modifiers, it's a little bit difficult to quantify what those structural changes are. There's these two bands here, and you can see that they belong to these 4-member and 3-member ring structures. They were identified very early on. Silica glass was actually first measured right after Raman made his discovery back in, I think, the late 20s or early 30s. And they thought that these sharp bands, they said, oh, they're too sharp. When we see the other bands in glass, they're quite broad. So they thought they were defects. They thought there's something else in the network that's broken. So they called them the D1 and D2 bands. The most widely accepted interpretation is that they belong to these ring structures, but I will say that there are still some people out there that don't think that this is a totally 100% accurate assignment. We have this cage rattling vibration, and for pure silica, we have these two small bumps, which are seen here around 1080 and around 1200 or so. These belong to the T2 mode, where you have pinching of two parts of the tetrahedron and an extension of the other. So you have sort of a motion like this. So as two go away from each other, two go towards each other in the tetrahedron. And then a symmetric vibration of the Q4 band here. And we mentioned that there's some difficulty there. How they came up with models, or how they generated some ideas for models about this pure silica network, they looked at the system SiO2, and these are different polymorphs of SiO2. With the exception of this one, this is metallic silicon, and silica glass at the top we just looked at. And they said, this envelope here, it's awfully similar to some of these different polymorphs, cristobalite, tritamite especially. And when you look with different techniques, you can see that some aspects of pure silica resemble cristobalite quite well, and some aspects of silica resemble tritamite quite well. And you can see that their most intense features happen to coincide with this broad band here. So various people have proposed a cristobalite or tritamite-like structure. Both of these have 6-member rings in them. The only other thing I want to point out before leaving here is that stishovite only has a couple peaks here that are strong, but its most intense feature is at quite a higher wave number from these other minerals. It's because, in this case, stishovite is the high-pressure form, which forms silica octahedron. So typically when we go to high pressure and we start to see or start to interpret 6-fold silicon, we get a band up in this part of the spectrum. So one of the main tools, a lot of the basis for the interpretation of glass comes from looking at the minerals. But there's obviously big differences between the glass and the minerals, which you guys are well aware of, especially if you're taking Zanoto's class. So this is where a lot of the interpretation comes from. With that, I'm just going to take a 5-minute break before we go on and do a quick run-through of a bunch of different examples and a few quick notes on curve fitting. So I'll see you back in 5 minutes. Okay, in the next section, I'm just going to quickly run through a bunch of different examples. Very quick, just to show the applications. I don't know what you guys are working on now. I don't know what you'll work on in the future. So we're going to show a bit of everything. To show you what's possible with Raman spectroscopy and how we do some of the linking between the structural changes and the properties at the end.
Yeah, and starting next lecture, we'll pick out different glass systems and then just see how spectroscopy reveals something that's happening there. So there's some more in depth on some of the examples later. So this is just over.
Yeah, this is a very brief overview. If you guys are interested in doing any of the things that I show here, probably we have the equipment to do it over in the physics department. So I'm more than happy to experiment in new different techniques that I haven't have experience with on your glasses with you. So keep that in mind if you see anything that looks like it's relevant to your research. So the first thing is looking at a glass under extreme pressure. This is something I have the most experience with, actually. And you can see this is actually an image of a glass shard here, plus a few other glass shards, inside a diamond anvil cell. So this sample is sitting in between 2 diamonds and held in there by this gasket. And because diamonds are transparent, we can see through and use the diamond as a window to get to the sample. Since we're using our green laser light, it's no problem to get onto the sample and back out. And we showed our spatial resolution of a couple microns. So it's no problem. This is a 100 micron hole. This sample is probably about 50 microns. It's no problem to get half a dozen different analysis or even more on the sample. So what happens to pure silica as we increase the pressure? This is a nice study by Deschamps et al. They showed that as you increase the pressure, this, what they call the main band, these are bridging oxygen vibrations, shifts to higher frequency, as does our D1, our 4-member ring band. You can see also, unlike the 4-member ring band, this 3-member ring band doesn't shift. It only shifts a little bit, but it does show some movement. Also, this other vibration up here, the cage rattling, shifts to lower frequency as you increase the pressure.
So these are some observations they made, and then they quantified it by looking at the position of these bands. And this is just two of their many examples. Here's the main band, and here's the D1 band, the 4-member ring band. And you can see as you increase the pressure, you see a moderate increase, then quite a rapid increase around 2 GPa, and then it tapers off again. And so they actually use these two bands, plus an idea of how the frequency should change as the intertetrahedral angle is adjusted. And they came up with a model that compares this Raman shift here with the actual change in the intertetrahedral angle. And they said at low pressures, it shifts by negative 0.8 degrees per GPa, then it has this strong shift around -2 before it tapers off again. So this is one way to connect the bridging oxygen vibration with the intertetrahedral angle and what's happening with your sample. The interpretation for this has actually been added to recently, and they now strongly suggest that this is related to an alpha-beta transition. So you have 6-member rings. If they're nice out wide, then as you increase the pressure, 2 of the tetrahedral will swing inside, and they kink. So you get sort of almost a figure 8, but of course there's no bond in the middle. And that's what's happening in this case. Another glass that's quite silica rich are ultra low thermal expansion glasses. These have a lot of uses, but the key feature is that from -100 degrees to around 350 degrees, there's not much change in the expansion of the glass. So this is used for substrates for mirrors, particularly for astronomical telescopes, and for any measurement where you're covering a few hundred degrees around room temperature, and you need a very stable system. So the linear expansion coefficient is just how much this glass expands as you increase the temperature. It's quite straightforward, but the expansion coefficient is the inverse of the length times the change in length with temperature. If you look at most glasses, and there's some examples above here, the Durand type glass, you've seen this a couple times from Doris's work. This is sodium calcium silicate. What's the BK7? I don't remember. Optical borosilicate. Yeah, and you can see some other materials here, Corning glass, Macor, titanium diboride. They have a thermal expansion coefficient around 10. And for this, vitreous silica is around 0.5. So this is an ideal scenario where we have a very small thermal expansion over this quite wide temperature range. So very good for making these telescopic measurements from looking at things at outer space. They have a kind of an interesting preparation for the glass. It's very difficult to make a glass that's big enough for an astronomical mirror. What would happen if you had a huge volume glass the size of this table? You saw the picture here. It's the size of a guy. What would happen to a glass this big if you made it with conventional methods? You would have all kinds of strains and stresses from the surface cooling to the inside. So they have to make these glasses in a completely different way. And they actually inject a small amount of titanium with silica into these burners, and the gas is deposited layer by layer on the glass below. So quite a different preparation.
And other reason is that, like SL2, it's really the melting temperatures are really, really high. Because the titanate tetrahedra are just like SU4 tetrahedra and SU2. So you won't really have the furnaces to go to that temperatures and to make your products.
Nice.
So what do we see? Here on the bottom is our vitreous silica, as we saw before. We have these Q4 vibrations here. When you add a little bit of titanium, 7.5 mole %, you get this ultra low thermal expansion glass. And you see that as soon as you add the titanium, you get much more intense feature around 937 and around 1100. So this 1100 band is related probably to this Q3 species, and this 937 is probably related to the titanium. And you can see that this band is quite polarized. whereas these bands are quite depolarized, or vice versa. Sorry.
On the literature, well, you find different assignments, but some assignments gave the 1100 to Q3 units, just because the Q3 silicate unit does has a band there. But that's, I don't know, you're going into it why it's not a Q3?
No, I don't know.
Okay, that was an example that just by finding a literature assignment on the 1100 does make it true, and just looking into the properties of Moulton class, that you don't have much thermal expansion. If you do have non-rich oxygen, that usually is a way to have quite a change in the thermal expansion. And it's the fully polarized classes, the Raman and the SO2, which don't show changes, or which have the high temperature stability in their size. So just from the properties, this assignment is kind of non-consistent. The other thing is the rest of the spectrum. If you have Q3 units, then the cage rattling operation would look different, as we had seen before it shifts, and the whole network deformation modes at the 400. So that whole system would shift upwards. So the other bands are not consistent with having Q3 units in the class. In the Moulton. So the assignment of this 1100 band is quite different, and also the polarization. If I probably didn't give you those slides for Q3 glass, silicate glass, the polarization is different. It's not not as
strong,
polarized as you see it here. So in the end, that's what you see at the bottom, that it's both bands, the 1100 and the 900, are connected to titanate.
Yeah.
That was the.
So if you just look at the literature values, you might make this mistake, but actually they're related to this titanium. And once again, this is a nice example where a small amount of something added can really radically change the spectra. So you have to be careful of your interpretation.
And Ben mentioned at the beginning, it's the intensity of, the wavelength is important for a nice intensity spectrum of the excitation. The other one was the change in polarization. Titanate ionic table is much heavier than silicate, and it's much more polarizable. So all the band vibration that involve titanate and oxygen, they are much more polarizable than the SAO bands, and that's why the 7.5% of titanate in this class just stick out in the Raman spectrum.
Yeah.
I don't know, do you show the infrared spectrum? Because they don't stick out in the infrared.
I show the absorption coefficient. This?
Yes. So you don't see much difference. Yes, there is the difference with the titanium band, but in the end, and here in the infrared, you see there's no sign of Q3 units. So in both the Moulton and the SO2 class, you see the typical infrared spectrum of Q4 groups.
Yeah. So this is a nice example where Raman and infrared complement each other, and I think in the classes after we do the experiments, Doris is going to go through many more examples where we have all the different spectroscopic techniques joined together. So that's a nice one. Here's a nice study where they looked at borosilicate glasses which have had iron to them. And this is another case where
even just 5% iron creates another band that sits right on top of these QN bands. So they had to model the spectra and make this, do some sort of curve fitting to look at this band, which obviously increases as the Fe3 plus increases. So they changed the redox in these glasses and have at the top of this here really high concentrations of Fe3 plus.
Here, as you can see, there's almost no Fe3 plus in the glass. And this is a case where they area normalized this part of the spectrum. They chopped this out and area normalized these bands here to look at and determine quantitatively how much Fe3 plus relative to the total is in their glass. So you have strong bands that overlap the QN species, and we are going to talk about curve fitting at the end. but you need some sort of model, and again, some sort of normalization to actually compare spectra with quite different compositions. And in this case, Raman is very sensitive to the redox of iron, and we can quantify this. Here is a sodium germanate glass with, sodium metasilicate, metagermanate. And if you just look at the spectra on the left side here, what we see are these small, again, Q4 vibrations, and nothing much happens as you increase the sodium content. What you do see is that around 20 mole%, we have a substantial increase in intensity, probably related to the formation of Q3 species. Typically, if this was a silicate, you would expect Q3 species to be forming down here at low sodium contents, but with the germanate glasses, there's a delay. If we go a little bit further, increase the amount of sodium here, 35%, we see instead of this little bump from the Q4, we get a nice intense shoulder which continues to grow.
And this is related to the Q4 formation, around 35%, 35 mole% of sodium added. If we look at the low frequency range, these are the bridging oxygen vibrations, where we see no changes here, we see quite strong changes in the 435 and the 520 band, where they shift and the 520 band becomes quite intense with small additions, but then it stays relatively constant for the rest of the composition. If we look at some of the properties, these changes actually correlate with TG, density, viscosity, and here's just one example. But we see almost no change, and then quite a rapid change to a maximum around 20% here, where we really start to break down the germanate network, and then it decreases again as you increase the sodium content. So what's happening here is actually in this case, the addition of sodium, or at least I think this is the accepted interpretation, is that as you add sodium, you're actually changing the germanium from tetrahedral to octahedral. And so as the germanium changes, you don't get much change in the network. Whereas once you really start to break down the network and form Q3s in these lower QN species, you have quite dramatic changes in the viscosity. This is a nice example of high temperature work. It's in an borosilicate glass where they've added molybdenum. And this is, instead of composition now, temperature going from around room temperature to 1,000 degrees. And you can see that everything sort of overlaps. This is perhaps not the best display of these spectra. But this band, if you plot the intensity with temperature, you can see that their assignment is related to molybdenum oxygen vibrations. And you see almost no change in the intensity, quite a rapid increase before a decrease at higher temperature. And their interpretation is that it increases when you have the phase separation of this sodium molybdenate. And you get small amounts. At the maximum intensity, you have the most separation. And as you melt it, you re-homogenize the system and get rid of those that sodium molybdenate phase. And the intensity of the band follows that. So Raman is really nice for phase separation. Here's another example. This is of sodium aluminum phosphate glasses, phosphosilicate. Here's the composition here. And they noticed that as you added small amounts of phosphate, you had quite strong changes in the high frequency zone. You have the addition of these peaks. And instead of just having the Q3 and Q2 bands here, you also saw a shift of this to lower frequencies. And they identified these additional peaks as these phases here. Then they decided to follow this phase separation through time. And they saw that for this specific composition, the 6% of phosphate added, you saw huge growth in this low frequency band and the disappearance of these guys in the middle. And what they said is that we're actually dissolving this guy and phase separating this guy in the system through time. They went a step further and they tried to quantify how much phase separation was going on and what was happening at high temperature and low temperature, because they got different results depending on the quench rate. They use this, the Avrami equation here, which just looks at the extent of this reaction. In this case, it's the extent of phase separation between those two sodium phosphate phases. And they get quite different curves. So this is time here, and this is different temperatures. At high temperatures, they get sort of a concave behavior of the reaction extent, the phase separation. And here at lower temperatures, they get quite a strong, rapid increase in the reaction at very short amounts of time. And what they said is here, the exponents, when they fitted this Avrami exponent, when it's close to 2, it suggests crystallization, and when it's around 1, they show it's related to spinoidal decomposition. So their interpretation was that these curves at high temperature, where the reaction is quite slow, much slower than these guys at low temperature, which is the inverse of what you would think, that this is related here to crystallization above the solvus, but when you go to low temperature, you're down in the spinoidal field where these guys stay separate. And they can actually follow the kinetics of this with time using the Avrami equation. So they can very clearly characterize the differences between these two processes. Another example, I actually quite like this example. This is apatite in a borosilicate glass. Apatite is a calcium phosphate. And all of these spectra are taken in glasses where they've mixed a little bit of apatite composition, calcium phosphate, into the borosilicate. And they've annealed the glass for 2 hours at the various temperatures you see here.
They also added a little bit of neodymium. So this glass composition has actually been proposed to use for the storage of nuclear waste. And the neodymium that they added, a small amount of neodymium, was used to mimic the fission products from the reactor. And what the idea was that if we can separate these fission products into the mineral phase, into the crystal phase, then we can isolate them from the glass matrix, and they'll be more stable than the original, just storing them in a glass in the original case. So their question ultimately was the neodymium actually removed from the glass, and was it actually stored in these apatite crystals that are grown in their glass ceramic? You can see that the spectra is quite complicated. You can see also that there's this, as you increase the temperature, there's this sharp growth of this peak here, and there's some other sharp features. These are what you would expect of those crystalline spectra, and we saw a few examples. But you get a very broad bands related to the glass as well. So we have to unmix the different spectra, the different contributions from the mineral. And we know that minerals have a really intense Raman signal. You can get a really good spectra of a mineral in 10, 15 seconds under optimal conditions. But for a glass, you need much longer to get the same clarity in the features. Whoops, I pressed the wrong button. No. Where's the presentation? There we go. So, how do we do that? What they did was use a linear combination of the spectra of the different materials. So here's the spectra, the intensity of apatite. This is this red spectra here. The intensity of the glass that has neodymium. This is one of their starting materials. So this is the initial glass with the neodymium in this blue. And the final is the neodymium the glass without neodymium. This was their goal. And here is neodymium-free glass that they looked at. So they did a linear combination of these three spectra and used it to fit all these different spectra annealed at the different temperatures. And what they showed is this. As you have increasing annealing time, what you get is for short times, at low temperatures, you get almost no apatite formation, so this isn't good. But as you hit above 640 here, you get really a large signal from the apatite. And this is quite large as a result of this difference in scattering between the mineral and the glass phase. On the opposite side, what they wanted is the glass without neodymium, so this gamma. And what they showed is that, yes, the initial glass with neodymium, it does reduce
its intensity, its proportion of the spectra does drop as you get the crystallization of the apatite, but you still get only a small amount of glass without neodymium. So it kind of didn't work, but it's a good idea. So if you wanted to actually change this from just the coefficients to the actual concentrations, you would have to do something else. You'll have to do some point counting or something else to actually translate these to, from coefficients to the actual concentration of the material. Doris showed this before, but in sodium borosilicate glasses, and particularly systems with water, you get a lot of overlap of the band features. So we need some methods for disentangling the overlap of boraxyl rings, boraxyl rings and silica vibrations. And this is just to remind you that we need some further tools to distinguish these things. Here is pure silica. We've seen this a few times, hopefully you recognize it by now. And as you increase the boron content, you get quite a big changes, particularly around 800 here. And these bands are at 770 and 807 are associated with 3-member boron rings attached to other boron rings. Is that correct?
Yes, and if you look at the literature now, he's a silicate guy, so he says 3-membered boron.
Yeah.
The original papers on the boron ring, they were counting the oxygen and the boron, so they say it's a 6-membered ring. So the boron class people and the silicate class people just count the members of the ring differently, just that you are aware. Because if we have borosilicate classes where you have silicate and boron rings, it would be good to use the same nomenclature for both type of rings. I just want to mention that. So.
And the other key feature is that with boron, you get 3-member planar rings, 3-member planar units of BO3 versus BO4 tetrahedrons. So we don't usually, I don't know of any paper that suggests this kind of configuration for silica. So when you mix them together, it gets complicated. But these are still network formers, even though it's not a tetrahedron.
Yeah, but the tetrahedron, the BO4 tetrahedron, it doesn't have a non-merging oxygen.
Okay.
That's as a chemist, you know, it's the BO4 minus, the negative charge is the boron atom is in the third group. So by having a fourth oxygen, there is a negative charge on the boron, kind of. And it only gets three-quarter of a charge from each of the BO4, and then 4 times at the end it's 3 full charges. But it's not a localized non-rich oxygen. So that's where in some papers you find the distinction between the sodium ion that's a charge compensator and one that's a non-rich oxygen compensator. So that's the kind of, yeah.
Another complication
and that's the Coolberg oxide anomaly. You probably have heard about the extrema and the properties as you form the BO4 groups, because you have a higher degree of polymerization as you add modified oxide, which is in contrast to phosphate and silicate classes. Makes the Boyd system the more interesting, because you do have these different units.
Yeah.
And then if you add more modifier, you create the non-rich oxygen on the BO3 groups. And there are few crystals where you have non-rich oxygen on the BO4, so it's not totally wrong. But we only we just tried to prove that we do have those tetrahedral orthogonal units with 2 non-rich and 2 rich in tetrahedron. It's a bit complicated because we have to find the right method of doing that. And there's some discussion, some believe us, some don't. So we continue on that, but there are crystals with pyroborate and orthoborate in the tetrahedral form. So there are crystalline evidence for the occurrence of those groups.
Yeah. This is something else you can do. This is a mechanical example where they've indented the sodium borosilicate glass. And you can actually pick one of these bands. So if you know your indenter, for instance, shifts the intertetrahedral angle to smaller angles, you're going to see a shift in the band. So if you measure, you pick one of the positions of one of these bands and you things like the intertetrahedral angle. You can look at other structural modifications by mapping across the surface of your sample. These spectra take a very long time. You will have a day or quite a while, depends on how big an area you want to cover and what kind of spatial resolution you need, but they're much more involved. But still, we can use Raman to look at the mechanical properties. Another thing, I know you guys are mostly glass people, but in case you have different crystalline phases in your glass ceramic, you can also look at phase change. This is an example I'll quickly go through from diopside to encetate. These are minerals now, not glasses. And the biggest difference in the two structures, whether you have a monoclinic or an orthorhombic structure, is just actually the kinking between this chain of silica tetrahedron versus the other one. So in orthorhombic, we have one chain with slightly different angles and slightly different bond distances to the magnesium in here. In the other case, we have two chains that actually have the same intertetrahedral angles. This is from XRD, where they actually measured the oxygen-oxygen angle. I'm not so much of a mineralogist, so I won't tell that, but it's a measure of this intertetrahedral angle. And they show that when you have two chains, as you go from two magnesium to a magnesium, you add calcium, and going, this is the calcium-rich member, magnesium-rich member, you have at some point a breakdown in the two chains where they collapse and become the same, as seen in the monoclinic structure here. So here with XRD, we see a dramatic change with the phase change. We see a dramatic change in this angle. With Raman, here's the Raman spectra of the same composition. So this is diopside rich, this is encetate rich. So here we're going from diopside rich to encetate rich. And you see that these guys with two chains, you show a splitting of the strongest bands in Raman. And when they look at, across this compositional suite, when they look at the shift in the position of these, you actually get quite a nonlinear shift. And you can draw this nonlinear shift right to the point where you get this phase change. And they collapse into one band. And they did a model of two curves for the two chains and one for the other one. And it shows that the sensitivity of Raman, we're actually seeing these bonds here flex and change and not just collapse in a dramatic sharp change here. So the Raman is much more sensitive to these small changes in the bonds and how much force you place on them. Here's an example of a fluorescent band. We know that Raman bands don't change. You can shift the laser excitation wavelength and the Raman band won't change. The positions are identical. But of course we have some fluorescent species, which Doris gave some great examples. Here's the different wavelengths going from 488 ultraviolet to the green wavelength here. And this band, this feature changes from, you can see it's quite strong, from here around 500, well actually 356. With a blue laser, it becomes 993, and with the with ultraviolet, it becomes around 2000. And you can actually convert from this relative shift to an absolute shift. So in terms of wave numbers, we shift 628 and then 1065, but we can convert that to actual nanometers, and we see that depending on what your excitation wavelength is, this this wavelength of emission of this fluorescent signal, it stays the same. So in all cases, you can back calculate the terbium fluorescence, and it ends up being at 542 plus or minus 1 nanometers. So this is one test of, another test of the bands that overlap. If you change the wavelength and they shift, you maybe have some fluorescence in your sample.
And the terbium bands, as we said with the fluorescence, it's very up so they, before F orbitals are shielded from the direct environment, so they're kind of small. If you have manganese or copper, you can have a very broad fluorescence and you don't see any spectrum, and you know that it's fluorescence, but they are kind of sharp bands, and they might look like a structural band in Moulton if you just measure at one wavelength. And you might be looking for the literature and oh, where's this 900 band coming from? But that's when just check with a different wavelength. If it moves, then you can ignore it for your structural interpretation. If it doesn't move, then you have to find out what it is. It's part of the structure.
Okay. Our next example is a sulfophosphate glass. And it has this composition. And this is from Doris, so she's published this work, so if she wants to jump in, feel free. But the idea was that they exchanged this zinc for manganese and looked at the structural changes as they followed the addition of manganese. So in the spectra, as we go from 0 manganese, so all zinc, to 35% manganese, we don't see a whole lot of change, but there are some subtle changes here in the shoulder where we might expect a Q0 species. What they saw when they looked at the properties is actually the hardness and Young's modulus. As you add magnesium, so 0 magnesiums over here, as you add significant amounts of manganese, not magnesium, you increase the hardness by 50% and you increase the Young's modulus by about 10 GPa. If you add, in addition to the manganese, also some iron, you can enhance these properties at very, very low manganese and iron content.
And a lot in this paper is on manganese and iron. They are both in the divalent and trivalent side. So we tried to stay reduced and we have only 2+, but we didn't succeed. So we also do have a lot of trivalent. If we do have trivalent, then we add more oxygen, then we do something to the network. And another thing is that you have, that's on the slide, some preferential sites for the different cations. And this glass belongs to the invert glass, so it's an ionic glass. You would have orthophosphate and sulfate tetrahedral, which are not connected by any covalent bonds to the network. We have diphosphate groups, but it's only P2O7 4-, so it's not connected to a network, to a glass. So it's only the cations that connect to these anions. So low melting temperatures, OGG. And apparently the phosphate and the sulfate, you have zinc and sodium ions, they bond preferentially to one or the other. And we see that after crystallization that you get one sulfate, one cation connected to the sulfate and one cation connected to the phosphates, but also with some of the bands, the way they shift, it's different. But it depends on the feed strength and the mass of the cation that's at the other end of the non-rich oxygen. And so we here on this side, for the sulfate, we had to fit 2 bands in the end. One of sulfate connected to the zinc cation and one to the sulfate connected to the sodium.
So that brings us to the last topic, which is just a couple slides. I'll try not to keep you late, but curve fitting. And you'll see this a lot, and you'll see that we can assign species to all the different vibrations under this spectral envelope. And let's talk about some of the issues. The first is what kind of curves these are. And for crystalline materials, we typically use a Lorentzian line shape, and here's the formula for the intensity of the Lorentzian. But for glasses, the best fit, I don't know if you remember at the beginning I showed that you can mix these Lorentzian and Gaussian combinations. Sorry, here it is here. They've done for glasses, this is again, I think a calcium metasilicate, but they showed whether they fit the line with Lorentzians, full Lorentzian curves or full Gaussian curves, and they show that there's quite a big difference when you try to use Lorentzian curves for glasses, but when you get down to much more Gaussian curve-like distribution, you have almost no change in the actual fit. So this is one argument for using Gaussians in glasses. So there's three main parameters for any peak, whether you're using a Gaussian distribution or a Lorentzian distribution or some sort of other distribution for the line. And that is the full width at half maximum, its position or its center, and the intensity of the peak. Of course, we only care about relative intensities. For our example, our original peak here in the mineral sandbornite, which I fit with the main peak with one Lorentzian curve here in yellow. And there's also a little tiny bump here, which I've had to put in another peak to fit. The circles here are my actual data points. So you'll see that the model, which is just the sum of the yellow plus the green curves, it becomes this red model. It goes right through the center of my actual data points. And you can see that there's some mismatch right at the top because our spectral resolution is limited to a couple wave numbers, but the peak is in between there. So we normalize this peak to 1, and then you can measure the width at half of the maximum intensity. This is the full width half max. And then you can look at the shift in the wave number as you go away from the center. And these are the equations for actually calculating the shape of that line. But know that the three main important factors for looking at each peak are its full width half max, its position, and the relative intensity. And those are the equations for actually determining them. Luckily, there's a lot of programs for this, so you don't have to do it all by hand. The last feature is a lot of spectra will be published with the residual. So this feature down here, this purple line, is the difference between our actual data points and this red model as it goes through. And you can see there's almost no residual for most of the spectra except right at the peak. So a little bit of a wiggle in the residual is just because of the resolution of the spectrometer and the difference there between the model and the actual peak. If you try the same spectra with a couple different lines. So this is an old study that gets a lot of citations. It's curve fitting for glasses. If you take this envelope, which it covers a couple hundred wave numbers, you can see that there's this shoulder and a main peak here. If you have just two peaks under this curve, you can see that the residual here is quite erratic. It's quite large. So chances are this tells us that there's another peak required to fit this envelope. So in B and C here, we have 3 lines and then 4 lines. And you can see that the residual doesn't really improve as you increase the number of bands. So when in doubt, keep it simple. I would just use 3. There's another problem with this fit is that you have this one tiny guy under another big peak. Usually that's indication that it's probably not the best fit and that you need another peak in there as well. But you shouldn't just fit a small peak under something big and wide because you need to fit the spectra. And I'll go through my bottom lines for curve fitting in the middle. But basically for glasses, the main point is that we use Gaussian line shapes, and you should try to use as minimum number of lines as possible unless you have a justification for why you're putting bands in a given spot. Just a few more examples. You can see this sort of envelope is quite common. Maybe we have a Q1 or a Q0 here, and a Q2 here, and some Q3. If we just use 3 peaks, and we assume there's only 3 QN species, we can't fit the spectra very often. So we need something else there, and that something else is something that is again debated, so I'll leave you to make up your own mind for it. But we can see some other fits here. So here is 4 peaks. This one is not too bad. You can see the model generally fits. There's a slight mismatch here, but generally fits the overall spectra shape. If you change the shape of the curve to Lorentzian or Vought and use the same 4 peaks, we can see that you start to get some mismatch with other peak shapes. And that's the same as we saw in the last pane, where using different Vought and Lorentzian peak shapes doesn't really work so well for glasses, in my opinion. So I'll end with just a couple bottom lines. Overall, when you put peaks under your spectra, this is a barium disilicate glass. Again, the red is the model. The circles are my actual data I measured from the Raman spectrometer. Down here is our residual. The overall shape and number of peaks should mirror the spectra. So we have a nice sharp intense peak down here, we have one that matches it. We have the main peak in the middle here, it matches it. Then we need something else to fit in this shoulder, and this, if you look closely, there's a bit of an inflection here. We need some other features in there. So bottom line is that your peaks and the peaks under the curve should follow the relative intensities of the spectral envelope. That's the number one point. If you have little peaks inside of big peaks, then chances are that's just there for the fit, and it's a mathematical fit and not actual conscious thinking of what those bands represent. I always say the minimum number of peaks should be used unless you have an explanation for those additional peaks. There's lots of studies that put peaks in, but then they just add extra peaks to fill in the gaps in their spectra. Oftentimes, a bad fit is one where you don't have an explanation for those extra peaks. Everything that's in here, I have a reasonable explanation for. If you have extra peaks, they're shifting and having an impact on the structural features and will probably change a little bit the interpretation of the spectra.
And if you have a glass series of 10 glasses with composition or temperature with anything.
Exactly. The best way is to look at a glass compositional suite to see how the bands shift as you add these modifiers and other features. That'll give you an indication of where new bands pop up. Exactly. Use a consistent fit the whole way through. If you just decide to change your fit at 50% silica and have one series fit for the other and one series fit, probably your model is not so good.
To fit the same 10 glasses 5 times until you have one set of fits that fits all 10 glasses, then you have to do it 5 times. Just go to the next cycle and see if this number of peaks is sufficient, and if you get a consistent fit. It might just take another round of fitting, but eventually it should be consistent.
Yeah, and it should be consistent for your entire temperature range, pressure range, compositional range, redox range, whatever you're looking at. It should be consistent. The last thing, and something that's overlooked, especially by people who publish a lot of papers, is that they don't always explain how they make their background. We saw that there's a huge slope at low frequencies below here related to the boson peak. This is actually the boson peak after you take off a background. Whatever you do, explain clearly how you've removed the background to get to the point where you can make this fitting. Explain the intensity correction, and you might do an intensity normalization when you show the whole spectra, but when you just look at the QN species, you might you'll probably area normalize it to get the proportions of the QN species. So explain exactly how you've modified the spectra from the raw data to get your structural model. That's the bottom line. This is this is an IR spectra, but the point is this. Or UV vis? Okay.
Yes, but you see it applies to any spectroscopy.
Yeah.
It doesn't only for Raman, so UV vis is for infrared.
So on the left side you have this nice broad feature, and maybe we want to put some curve fits under there. And you see, maybe you change the composition, you get a nice shoulder. When you have broad features like you have in glasses, it's really important to have a structural model in mind, that you test your model you test your model with the spectra. Because sometimes it could just be an elephant being eaten by a snake under there, and you don't know. So bottom line is, when you put a peak in, you should find an assignment. And even if that is just saying what other people have made for this assignment, but know what you're actually putting under these curves. Have an idea of what structural unit it is and what you would expect based on how you're modifying your composition or your experiment. So that's my short note. At the end of the day, Raman is really diverse and really useful. Hopefully you've seen that we can use it for many different types of compositions, phase separation, in situ crystallization. It has excellent spatial resolution down to a couple microns, more or less. Most of the time for glasses, for silicate glasses, it's non-destructive. For biological samples, it gets a little bit more iffy. There's almost no preparation required. If you quench a glass, you can take it, throw it under the microscope, and measure it as is. So you're using free from modification. You don't have to manipulate the sample to get a spectra. Most of the time, for good quality spectra, it only takes a minute. So it's fast, it's easy, and it's very useful. Because it uses visible light, we can look at high temperature and high pressure without problems. So long as you can make a container that has a visible window where you can shine light onto your sample, you can get the Raman signal from it. So it's great under a very, very wide range of conditions. The difficulties, as you've seen, is that sometimes and many times it's difficult to quantify. So you really need to have a model that you're testing, and I showed you the example of looking at and collecting the bridging, non-bridging auctions to test whether your QN speciations make sense. It's very complementary to other techniques and provides often different information from them. I would just say that there's a lot of inconsistent treatment of data out there. There's a lot of papers with a lot of different fits and a lot of different ways of doing things. So sometimes one of the cons is that people treat their data very differently and it's hard to compare. So be aware, hopefully now, of the major issues that arise with Raman spectroscopy and how you can use it. I have one slide here with references. I'm going to update this, and when we upload the presentation at the end of the day, I will update all the references and you can see where I've got everything from this presentation. But I'd just like to thank Doris, my former supervisor Grant Henderson, Daniel Neuville, and Jean DeBessy, who contributed some of the slides you've seen today. Most of it is not my own work. So thanks a lot, guys, and thank you for watching.